Yeah, sorry 啊，刚才迟啊，因为我们在讨论 FYP 的东西，明天要交，所以不要紧张。Okay. All right. We'll continue with compactness. Okay. So what we have so far, here. What do we have so far? So what's true in topological space? Which compactness imply which? Which compactness will imply which? Limit point compact implied by.
No, the other two implies limit point.
Huh?
The other thing.
The other two implies limit point compact. So sequential compact. 有没有讲完 implied by 吧 by what? Okay. And then metric space, what's true for metric space? Which direction? This direction, huh? Okay, today we will see that actually all three are equal for metric space. Okay, but to do this, we need to introduce a notion for totally bounded. Okay. Have you seen this notion in MA or not? No. Okay. So in metric space, we define something called the totally bounded. Okay, a subset A is totally bounded if for every epsilon greater than 0, then A could be bounded by finitely many epsilon ball. Okay, finitely many. Some. Okay, this is a bit similar to compactness, right? A bit similar. Okay, every open cover have a finite subcover. A bit similar, but for that case, you need to sum for arbitrary open cover. Okay. But in this case here, you just look at finitely many union of epsilon ball here. So this is true for every epsilon. Okay, true for all epsilon, no matter big or small, no matter how small it is, okay? You can just use finitely many, okay, to cover your A. Okay, one very easy consequence from this definition is a totally bounded metric space is actually, you want to guess? Is bounded. Okay. What is bounded again? What's the definition of bounded? Okay, use ball. Okay, everything contained inside a ball. But this one, we are talking about a whole matrix space, right? Okay. You cannot talk of a larger ball, right? So you can really prove from definition. What's the definition of bounded? All the distance is less than some number m. Yes. Okay. Okay. So can you deduce this letter m or not from this finite ball here? Can you deduce? You deduce a m number m from this finite ball condition here. Yeah. So how? I mean, do you have any epsilon to start with or what? You want to use totally bounded condition, right? We need to start with some epsilon. It's true for all epsilon, right? Okay, yeah. So let's choose some finite point in x such that b1 of xi will cover your x. Okay, so meaning what? So how do you imagine this picture here? You got x, and you got x, and then you got finitely many x1, x2, right? x3, and then s4, s5, like that, right? Okay, let's say n is 5. So the ball of unit 1, okay, can cover the whole space. Doesn't matter. This one depend on metric, right? Yeah. Okay. Then what m you can pick here? The m that can bound every distance you had, every two. Hmm? Hmm? Biggest ball. So all the ball here is radius one 啊，虽然你看到有些大有些小，其实它们是同一个 radius. Okay, we really only pick radius one ball here. What's the magic number here? 5. Okay, so the magic number is this. Let's pick 2 plus maximum. Okay, between all these center. Okay, you can do this, right? Because we only have finitely many center here. Okay, the claim is so the claim is this. So let's write down this claim here. So for all xy in x, okay, dxy less than n. Okay, so you use triangle inequality. So how to apply triangle inequality here? So how to think about triangle inequality? So I give you hint here. Okay, we work backward. Where does 2 come from? 2 is no, not radius. Radius is 1. 2 is okay, it's diameter. Another way to think about it, 2 is 1 plus 1. So if you want to use triangle inequality, right? You got 1, you got 2, 1, you got 1 maximum. Can you think of that triangle inequality here? How? Huh? How to link? Huh? This x is covered by one of the ball, right? Okay, link it to one of the ball, let's say xi. And then y potentially live in the other ball. So let's say we call it sk. Then can join or not? Can join like this. Huh? Okay, so we could like add the distance between xi. How can not use twice triangle inequality? Okay, so the ball distance we got 1, ball distance we got 1, and then we surely this number here is less than the max of all the distance. between the center. And then this is the M we pick. Okay? Make sense? Make sense? Any question? Make sense? Okay. So the M we pick is a finite number. Okay. Once you fix your V1 ball, then this is finite already. Okay, because there's only finitely many center here. Okay. So far so good. Okay. Okay. But is it true that every bounded space is a totally bounded space or not? So meaning if all your distance is within some m, is it true that for every epsilon you can use finitely many balls, okay, to cover your space? Is this true? Is this true or not? Not true. Why? Any examples? A bounded space, but not totally bounded. Can give some examples? Yeah, can give some example. Metric space, still live in metric space. Bounded, okay, but not the, yeah. Any idea? Any idea? Tony, any idea? Discrete matrix of some infinite space. Okay, so do you want to give a infinite space? You I ask you. 那你给一个 UM，你看你考试就没有给我看到 example， 就扣你分了，是不是？是不是？对，就叫你给一个 space，你又给我讲你，给我一个，快点。Okay, thank teacher, good. Actually, this is the lecture, not example. 很好啊，你看，乖乖选一个不是很好哦。Okay, consider Z with a discrete metric here. How is it bounded? How is it bounded? Okay, you can bound this set using, let's say, radius 2 ball, right? So discrete matrix means, okay, let's write down the definition. Dxy equals to 1, okay, if x not equals to y, 0 if x equals y. Okay, it's different than we got 1, not different than 0. But it's not totally bounded. Okay, so meaning you want to find an epsilon such that there's no finite ball can bound it and contain this set. Okay, can you think of one? 1/2. 1/2. 1/2. Let me think. 1/2. Did you cover anything or not? No lah. I mean, like at least you need to cover some point, right? So let's say 1/2. Try. So let's try ball of 1/2 x. Yeah, I think so. Yeah. So every x, you have this 1/2 here. X surely there because 0 is less than half. Okay, but you remove any of this ball, right? There's no more ball can cover your x. To cover the other x, how big is your radius have to be? At least one not enough. You are not touching the one. Have to be strictly larger than one, right? Because if you're larger than one, actually you include everything already. because different point has distant one. That's it. To every point is the same distance. Okay. So if you are radius one, because you are open ball, right? So you're not touching one actually. Okay, so you also can try this set B1 to cover your set. Also don't have finite subcount. Okay. There's no finite sub. Okay. Okay. Next. A very technical lemma here. So actually totally bounded is a hereditary property. So meaning what? Meaning any subspace of totally bounded metric space is totally bounded. Okay, every subspace of totally bounded metric space is totally bounded. Okay, should we prove this? Maybe we just draw some picture here. Let's draw some picture. Okay, so let's say we have a totally bounded metric space X. So this one call it X. Okay, and then let's say we have subspace Y here. So let's draw. This is Peninsula Malaysia. Okay, we want to show that this piece here is totally bounded. Meaning for every epsilon, there's finitely many ball that contain this. Okay. Well, we have to use assumption, right? Okay, S is totally bounded. So let's pick any epsilon. Okay, let's pick any epsilon. Okay, so we try to find this finitely many epsilon using our whole space is totally bounded. Okay, let's do it. So let's say we have some xi here. So let's say x1, x2, 3, right? Okay. Then there's ball coming from the finite condition. Okay, that can cover our y like that. We surely can do this, okay, because x is totally bounded. Okay, so let's name this ball here b. Let's say b epsilon x1. So we fix. Then this one b epsilon x2 and b epsilon. Let's see. Yeah. Okay. But if if these three ball are good ball that can have finite number that cover our y, right? But the problem is maybe sometimes the center is not inside our set. Then, for example, the third ball, we can't say that this is one of the possible candidate we use, right? So is it still possible? You see, although this ball maybe lie a bit outside, right? Is it still possible to cover this part with finitely many balls? Is there a way, okay, to cook out the finite number of ball, okay, from let's say this 3 ball here? Is it possible? intersection. So how kind of intersection you have to look for? You mean check the intersection of y and the last ball here. Okay. But this bit here, you see, if you look at this bit here, the intersection between this ball and the other ball, actually already covered by some finite ball, right? Okay. Do we need that part? Yeah, try and think about it. See, can you cook out some other finite ball or not? Okay, so there's a magic analysis miracle here. Let's say, right, instead of epsilon over 2 ball here, right? Sorry, epsilon ball here, maybe we pick a smaller ball. When you see epsilon over 2 in analysis, what are you expecting? Huh? Epsilon over 2. How many time triangle inequality? One time. Maybe epsilon over 3, you need three piece. Okay. So maybe this division, right, actually signaling you how many triangle inequality to use. But actually, if you don't use epsilon over 2, in the end, you get 2 epsilon. Does it matter or not? Doesn't matter. But if you get epsilon plus 2, then you have to cry already. Epsilon go to 0, 2 still never go to 0. Okay, so multiple of epsilon still okay. Okay, multiple of epsilon still okay. Okay, so the miracle here is like this. So you see, maybe the center is outside, but what we can always do is look at the ball of intersection with this epsilon over 2 ball here. Let's say we pick a point y1. Okay, so okay, let's do this one construction. Let y1 be in the epsilon over 2. Okay, so let's pick. So make sure that there's really something inside yi and this ball. For this one, y2. Okay. And then how big is it enough? Where the claim is I just look at the b epsilon. Again, twice the radius of what we had just now. Yeah, I claim that this is enough already. Twice the radius. Our claim is this is enough. These ball are enough to cover. So let's name this ball here. So b epsilon of y1, b epsilon of y2. Okay. Let's say if this is enough or not. Okay, we claim that this is enough. Okay, you just take twice big as big is enough. Same number. Okay, same number. So for sure, right? So for sure that b of epsilon over 2 of xi surely live in some b epsilon. Because your yi chosen is within epsilon over 2 with xi. So let's show this. So let's take y in b epsilon over 2. Okay, and then we want to see what's the distance between y and yi here. Okay, this is exactly the distance less than equal to the distance of y with xi, and then plus the xi with y. But y live in the ball of radius epsilon over 2 away from xi, so this is less than epsilon over 2. How about xi and yi? We pick from the ball of epsilon over 2 of xi as well. Okay, so it's also less than epsilon over 2. Okay, so this is less. So, but what? But this epsilon over 2 ball xi, right, already cover my y. Already cover my y. Not my wife, my y. Okay, my y. Okay, so my y is smaller than all union of all these ball. And then I compare all these ball. Okay, so consequently, these finite ball will this open ball be epsilon of yi. Okay, if we want to show it in the subspace case, right, maybe we intersect with y. Okay, in the subspace y cover y. Okay, so I can cover all the epsilon over 2 ball, but epsilon over 2 ball already cover my y, so I will cover y. Okay. Is that true? Does Sepang cover Lydia or not? Sepang cover Lydia or not? Is Lydia in Sepang? Because SMUN is in Sepang. You are in SMUN. Okay. So to contain you is enough to contain the school. Okay. 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 But something very weird happened in Rn. Rn is a very interesting case here. So a subset X in Rn is totally bounded if and only if it is bounded. So we have shown one direction, right? Totally bounded implies bounded. Okay, totally bounded implies bounded. So the thing left to show is bounded implies totally bounded. Okay, should we do this? What time is it? 3:35. What else I need to do? Okay, let's finish the metric space compactness equivalent statement within this hour. Okay. We got 4 statements to show. You want to see this? How about let's think of one specific case. Maybe we can generalize one day. Okay, so one direction is done. Here we just need the other direction. Bounded implies totally bounded. So bounded means what? Okay. Just now Adrian said contain inside a ball, right? Okay. If you are contained inside a ball in Rn, you can replace this ball with cube, closed cube. 对吧？那个适应对吗？你买拉布布的时候是放在哪里？没有买拉布布咩？你买盲盒的时候它是假卖，就是放在 cube 里面卖给你，对哈？那它里面东西是圆圆的，对不对 ？Okay, so you can bound a sphere using cube. Okay, so we just look at a general case cube. Can you show that a cube is totally bounded or not? Okay, so let's look at one example. Example which is just look at R. Okay, so what's the cube in R? What kind of cube you have in R? Closed cube. Closed interval. Okay, so let's look at some closed interval. Let's say -2 to 0 to 2. Let's say in this case. Is this totally bounded or not? Totally bounded, I have to show what? for every epsilon, okay, for every epsilon, you need to produce finitely many open ball. So open ball here is what? Open interval, okay? If I give you any epsilon, can you see that you just need finitely many open interval? How, Joshua? Hmm. Good. So you are saying that we use the epsilon to chop up the cube, right? Yes. Good. Okay. So should we do some examples here? Let's say my epsilon choose to be 正月写一个 epsilon，我们来切切看 irrational 又恶心哦，又拍啊，OK，好恶心哦，怎么办？怎么切？我找不到 over 拍的刀来切，over 拍怎么办？来，Joshua try your method，try your method 啊，Yeah, how many ball you need? Yeah, okay, okay. So distance of -2 and 2 divided by epsilon. So you need pi epsilon ball. So how do you place them? 1 and -2, 1 and 2. Huh? 4 pi. Oh, sorry. Yeah, sure. Definitely. 4 pi epsilon. Hey, sorry. Huh? Oh, okay. Thank you. 4 pi. Okay, 4 pi ball. How do you place the 4 pi? I think okay, a bit hard to calculate 4 pi. So let's change a little bit. Let's change one thing. So let's say you need 12 ball, huh? Okay, so how do you place this 12 ball? Yeah, this is the problem. Yeah, this is the problem. Okay, maybe 12 is a bit too many for a mathematician, huh? Just put 2 lah. Huh? Okay, how about 1? Because my interval is quite big. Okay, I think 1 is enough. 4 啦，just 4 ball only, 4 ball. 来，你算一下这4粒可以放吗？有够吗？够吗？试一下。Just now, Joshua said try -2, 2, right? So if you place 1 each, what do you get? You get up to -1 and 1, like this, right? And then also place 1 at -1. 也可以 try. So we got this one and this, and then this one, and 这边 so 有1个、2个、3个、4个。0 is not covered, right? Okay, so yeah, sure. Yeah, depend on how you put it. Okay, if you want to slightly move this a little bit, it's fine. But I guess there's no harm to put another one in the middle. Okay. Huh? Yeah, but the problem is I want you to think about how you partition. Yeah, how to partition your set. Okay, there's a few ways to do this. but the standard way, okay, if we want to introduce a standard way to cover, we'll talk about these lattice point. Okay, this integral lattice. Can you imagine in Rn, what are the integral lattice? Lattice built out by integer, integral lattice. For example, R2, what are the integer lattice? R2 来给一个 integer lattice coordinate. Yes, 1, 1. Okay, 2, 2, minus 2, 1, minus 2, minus 2. Okay, so the claim is there are only finitely many this kind of integer lattice point inside your closed tube. And then you can build ball around, then build ball around it. Okay, to cover everything inside a cube. Okay, make sense? Okay, so we got a general method written out in the lecture notes, but the idea is like this. Okay, you find this integral point, okay, and then build your epsilon ball. Okay. This integral lattice maybe could change based on your epsilon. Okay, maybe when your epsilon is even smaller, okay, then you need to find some other so-called integral lattice with respect to that epsilon. Okay, because our epsilon is 1 here. Okay, so the distance you can cover is at most 1. If the lattice is like, if your epsilon is like just now 1 over pi, then maybe you want to find integral lattice that looks like minus 2 plus 1 over pi, like that. Okay, makes sense? But the point here is you only need finitely many. Okay, open interval to cover. Because there are only finitely many such integral points. Okay, next, there's some setup to do before we have the final theorem here. So this lemma says that every sequentially compact metric space is totally bounded. Okay, so it says that if you every sequence has a convergent subsequence, then you actually can bound your metric space with finitely many epsilon ball for all epsilon. Okay, kind of strong, huh? Or if you have a convergent subsequence, then you can bound your set using finitely many epsilon ball. Okay. This lemma, right, suggests to prove by using contradiction. Okay, you can use contradiction to prove this. And that means you assume that it is sequentially compact. Okay, but there exists an epsilon greater than 0 such that the open cover of X does not have a finite subcover. Okay, cannot use finitely many B epsilon to cover it. Then what you can show is what can you show? If okay, what can you show is this will contradict with these with the sequentially compact property. You believe me? Do you believe me? Jingsen, do you believe me? 啊，我讲什么？我讲 OK， 我讲的是 OK，I say you should prove this using you can prove this using contradiction. Okay, so how do you do contradiction here? So you suppose that this metric space is sequentially compact. Okay, so meaning I give you any sequence, it has a convergent subsequence. But you at the same time you assume that it is not totally bounded. Okay, not totally bounded means what? There exists an epsilon such that you cannot have finitely many ball of radius epsilon to cover your X. Okay, somehow these two conditions will contradict each other. Is it possible? Contradiction means what? Because you need to contradict with some sequence statement, right? Then you need to think of some sequence that you can study from this ball here. Can you cook out a sequence from this ball or not? A union of ball that doesn't have finite subcover means what? Each of these ball must contain some point that's not in the other ball. Correct or not? If it is contained, then I can just throw this ball away, right? Correct or not? Okay. I want to try and discuss this. Okay. So let's prove by contradiction. Okay. So we will select a sequence in X. Okay. So how to choose this X here? So well, we just simply start with any point. Okay, next. We look at the ball. We look at the ball of radius epsilon around x1. Okay. We have infinitely such a choice because we assume that it's not totally bounded. Then we pick another one, S2. And then we can pick S3, again, such that it is coming out from the complement of ball of radius epsilon around x1 and S2. Yeah, and so on. Sn would be x in union of all the epsilon x. Okay, so we can do this because there's no finite subcover. Okay, we can do this. Make sense? 中意，因为要讲我们为什么可以这样做啊？为什么？为什么？什么条件啊？因为它不 totally bounded. Okay, not totally bounded. Okay. Yes. Ah. Sorry. Yes, this is infinite. Yes, we continue for every n. Yeah, we continue for every n. Okay. So, by sequentially compare, right, this Sn here should have a convergent subsequence. Okay, let's say it converge to A. Okay, let's say it has a subsequence converge to A. So what does it mean here? For large enough, for sufficiently large, JK, okay, we can look at what are their distance. There must exist two numbers that are arbitrarily close to A. Okay, arbitrarily close to A. Okay, arbitrarily close to A. In particular, we want to make it epsilon plus 2 close. Okay. In that case, these 2 points here, the distance will be less than what? Epsilon. But how do we pick this SI? We are picking this SI away from epsilon. Okay. So there's a contradiction. Okay. Because they converge, some points will be as close as A. Okay. Eventually, they'll move into some epsilon ball. Okay, but the way we pick these sequence is epsilon away from each other. 对吗？是 epsilon away 嘛？你看 ，OK, epsilon away from SE, epsilon away from SE and SE, and then 全部都是 epsilon away, make a point. Okay, but here says that 够远的话 actually there are two xi 是 epsilon close to each other contradiction. Okay, make sense? Okay. Okay. All right. We have, let's say, 3 minutes. Okay. There's one lemma that I want to skip here. So this lemma is the Lebesgue number lemma is true with sequentially compact. Okay, if you replace the condition we had for compact to sequentially compact, okay, it's still true. Okay, and I draw some nice picture for you to imagine the proof as well, so you can try and read it. Okay, so in this case here, we will start proving the Bose lemma here. So in a metric space X, compactness limit point compactness and sequentially compactness are equivalent. OK， 这是它们的黄金三角关系。Right? Huh? Yeah. So what are left to show here? What are we left to show here? Actually, not many angles we need to put in already. So, Eric, do you mind to remind us again? Limit point is the lowest. This one we done already. This one done already. This one we done already. So how many things we left with to do? Sequentially compacted to compact. Let's see. So if I know how to go here, can I come back or not? Can come back? 会回来吗？会不会回家？怎么回家？啊？ Compact, how to go from compact to sequential if you have this 4 arrow here? So we go limit and then go sequence, then come back already. But this one limit point go compact, can or not with this 4? 这样，所以下去下面先 okay, good. So limit point go to sequential compact and then go to compact. So really you only left with one green part, a green arrow to show here. Okay, so it remains to show that. To show that sequentially compact. Let's compact. Okay, so we need to do the upper cover things. Okay, so let's take and open cover C of X. Okay, then we need to show that this has a finite subcover. All right. So we have all these totally bounded stuff, right? So this is a matrix space. Okay, so this is a matrix space. Matrix space, or is it totally bounded? Is it totally bounded matrix space? Just now we showed that it's not always true, right? But what case is true? When your matrix space is sequentially compact. Okay, so okay, let's keep that condition later. So by okay, since X is sequentially compact, Okay, there are two things we can use here actually. There are two weapons we have. Okay, one weapon is X is totally bounded. Okay, second weapon I didn't prove to you is you can use Lebesgue number lemma here. So if you look at the Lebesgue number lemma, do you still remember what's Lebesgue number lemma is? There exists a delta such that for every x in X, okay, this Lebesgue number lemma depends on what? Still remember or not? Depend on the open cover we start with. Okay. So this delta depends on my C here. If you build any delta ball around X, it should live in some open set in your C. Okay, so this is the Lebesgue number lemma. So this delta is a number, real number, right? Okay. So we can use that X is also totally bounded. Okay. So can you imagine what happens now? So what happens now? So if you have a space X, Elon Musk, space X. Okay, so you have a space X here. And then you have an open cover, right? Okay, so these are your U. Okay, all your these ball and this ball. So your ball of radius delta C X. Okay, let's say the center is X. Okay, it's live in one of the U here. But if you look at all those ball, right? Really, you really need. Wait, 我在写什么？这个 totally bounded D bounded D. If you look at all these delta ball, this delta ball will have a finite sub cover. 看到答案了吗？有没有看到希望？大家再仔细看一点，再仔细看，再仔细看，已经看到希望了，大家看到企鹅。喂，Yes. So you see, you have an open cover U, right? Okay. And then you have all these B delta. B delta, what's the property here? Must live in one of the U. But totally bounded says what? If you look at all these B delta, right, you just need finitely many of them. And then these finitely many of them must live in some U. Then how many U you need? Just as many as you need for your B delta. Okay. Okay. So for every I in 1 up to n, we just pick ui in C such that this ui will contain B delta xi, the finite B delta xi. Okay, then this is your finite subcover. Okay, Anna? Okay. Okay, so you can see that how useful is Lebesgue number lemma here. Okay, you can make sure that your ball is living inside one open set, and then you use totally bounded to control how many ball you need, finitely many ball, and then you just look at a larger U that contain all these ball. Because the small one already cover X, surely the larger one also cover X. Okay. Any question so far? Any question? Okay, if no question, let's break until 4:11, and then we'll come back with a complete metric space.
画一下那个所谓那个我的网络给你们看出来。对对。还是会。不是，我没有关注我。
哎，我看一下你的三角形，你的三角链，
刚刚我们关去的。
你的三角链在那里。
哎，没有关注这个。
我们正了这些，
嗯
我们正过 compact 哦有，
嗯，
我们有，我们其实有正过这个去这里耶，
有，中间1、2、3、4就够了。
然后我们有正过 compact 去，没有，compact 不一定是个性好，对对对，shit，大概我就生气，
哦，
对啊。这里是过这个开头。不要。这个是你来说，还是我来说？
I guess okay. 用这个话是一件新的，我当时是好像是那个月前的那个I guess 还有要走沟通，我原本这个微博这个要是说这个。
正月，是不是你？是你讲那个，你不知道 MA2的，是你讲的。你现在看有没有别的分？
没有，它有些东西还是有点差别的，
对，肯定有差别的，但是我们这边会更 general。
感觉这样子有这个过程这里，
对，
它有点像个人会有，它可能一点
对，
好这个手势，
说的是什么？
因为 MA 很 particular，
啊哈，它是一个 RN。
然后我会来有时候在 RN hold 这东西哦，我会想着不 hold，因为我一直想着 Topology space。
Logical space hold 的东西 RN 一定要 hold。
对，就有时候
因为 metric space 就是一个 topological space， 所以 topology 要 hold 的东西 metric space 要 hold，metric space 要 hold 的东西不一定 topological space 可以 hold。对，只要我们这边 deduce for topological space 的， Symmetric space 什么意思？用什么？当然了，只是说帮你去想东西咯。
也是有用啊。
Yeah，帮你可能快速想到一些靠近的答案这样子。
那些生
每一个 matrix 都很多，
那些
但是我还没有见过。
哦，没有。
我要自己做。
哦，你不懂啊？
但是我想，这就是我的喜欢，然后来说玩东西。
快点，你摸，转水槽。
来，一堂。那可以有个 space 啊。来。就是它是一个这里面农地，然后有钱代表每次
没有，这没有。
啊，
是有偏见，绝对是有偏见。
然后必
巴西，完全没方面。
你没必要。
地方。
Hello. Okay, let's continue. Hopefully, we can finish everything before countability and separability today. We will do a little bit of complete matrix space. Okay, although maybe you will see in the textbook that complete matrix space is in chapter 5. Okay, but we will do it first half of it. Okay, to relate to this totally bounded, and then together with closed, the idea of closed, totally bounded. Okay, and complete and compact. Okay, so we try to link these ideas together. Okay, so maybe people was worrying about what's in the exam. So whatever before the last bit of chapter 5, we will put into the exam. Okay, and then the last bit of chapter 5, we will do it as a discussion, not tested in your exam. And we will do, my planning is to do the master presentation in class. Okay, so maybe the last few lecture, there will be master presenting, okay, their topics. Okay, so they will presenting topics related to topology. You will see topology in different area. Okay, in applied maths, in physics, and in different area of maths. Okay, so that's the plan for now. We will update again. Okay, so to talk about complete metric space. Anyone recall what's a complete metric space means? Okay, before that, I think we need one more pieces of ingredient. What's the key ingredient you need for completeness? Yes, again, Cauchy sequence. So a sequence Sn in a metric space XD is a Cauchy sequence if for every epsilon greater than 0, there exists m in n such that for every jk greater than n, esj and sk less than epsilon. Do you know what this means or not? What does a Cauchy sequence means here?
Okay.
Yeah, they get really close together. Okay, after some n. Okay, for every epsilon, you can find that they are very close to epsilon close to each other. Okay, if it is far enough. Okay, surprisingly, this definition is closely related with convergence. Okay, convergence says what? All the tail of the sequence will get really close to one number here. But here, it just says that the two terms from your sequence get really close to each other if they are far enough. Surprisingly, when they're close to each other, then you can deduce something about the limit. So first theorem, I guess, you will see in your MA, right? You should see every convergent sequence actually is a Cauchy sequence. Okay? Because the tail have to get really close to one number. So meaning you might think that, oh, maybe the tail are quite squeezed together as well. Okay? But the other direction is not always true. Okay? If you have a Cauchy sequence, maybe it won't converge. Okay, the point here is the point it converges to, right, might not live inside your space. They really get close to something, but that thing might not live inside your space. Then we won't call it convergent. Okay, when we say convergent, we always means that the point it converges. Okay, if it's unique, we call it limit, right? That limit actually live inside the space. Okay, for example, what? You can take a Cauchy sequence, okay, that really close to square root 2 in Q, right? Okay, then you converge to square root 2, but square root 2 is not a rational number. Okay, so in this case, we will define that a metric space is complete. Okay, complete if you add in all the limit point of Cauchy sequence. The limit point makes sense here. Limit point could be live inside or outside space. Okay. Okay, if it contains all the point that Cauchy sequence converges, or Cauchy sequence converges. Okay, then it is complete. So what things you know is complete? in particular from MA. R is complete, right? Okay. So what did you learn about R is complete? How is R complete? That's the definition. What's the axiom? Sorry? Name what name? Say one. Huh? Larry. How is R complete? Okay, so every non-empty, okay, very important, non-empty subset, okay, of R. So here is TFAE. I still got one more to say. So every non-empty subset of R, which is bounded above, has a least upper bound. So this is the least upper bound axiom, LUB. Okay, but here there's no Cauchy sequence, right? Okay, but this is equivalent to every Cauchy sequence in R converges. Okay, potentially you also need the Archimedean property here. Yeah, Archimedean property. Okay. So we won't present this proof. This proof is a bit long, but this proof is just MA1 kind of argument. Okay, you can find in this book here. So you can try and find in the Richmond. I think there's a very good written account here. Theorem 5.2.12. Okay, I think you should at least see once in your lifetime. Okay, we won't test this also, but at least you should see once, okay, in your lifetime. Okay, in that case, how about general subset of metric space? Okay, how about general subset of a metric space? Let's say we start with X to be a complete metric space. Okay, so meaning if you look at every Cauchy sequence here, okay, the limit will stay inside X, the limit point. If we look at a particular subset, okay, X, okay, how do we characterize all these complete metric space? Okay, induced metric here just says that I use the original matrix and put on my S. Then S is a complete metric space if and only if you contain limit point. Or what's the idea of containing limit point? S is closed. Good. Okay, S is actually closed in X. So if you are closed in a complete metric space, you are complete. Okay. Or if you are a complete subset of a complete metric space, you are closed. Okay. These two ideas are equivalent inside a complete metric space. Okay, for example, in R, okay, in R, if you look at closed interval, it is also complete. If you look at a Cauchy sequence inside a closed interval, you should be able to find limit there. Okay, so inside a complete metric space, these two ideas are the same. Yeah, let's prove this. Actually, not too difficult. Okay, so there are two directions here. So let's say we do this direction, prove that X is closed. So what we want to show is we just need to show that if Sn in X such that Xn converge to X, then this limit point here actually live inside S as well. Yeah, so contain all the limit points. Because this is metric space, I will just use sequence. Okay. So because this is a convergent sequence, right? Okay, convergent sequence. So we know that Sn is actually Cauchy. Okay, Sn is Cauchy. But we assume that S is complete. Okay. And S is complete. So what? So Sn will converge to some y in S. But can this X and Y different or not? Would it be different? Would it be different? Why not? Okay, so in metric space, the limit is for R unique. So X equals to 1. Is it hard to see why metric space is Hausdorff space or not? Okay. Okay. So if you take 2 points, just take the distance between x, y. So you need to make sure your distance between 2 points is non-zero first. If it's 0, then the ball becomes degenerate, right? Yes, that's the positivity. Okay, if it's 0, if only if x and y is the... Okay. Right. How about the other case? So assume that S is closed in X. Okay, we're going to show that it's complete. So meaning I need to check for any Cauchy sequence. Okay, we just let Sn be a Cauchy sequence. X. So we want this limit to stay in S or X. S, right? Because we want to show that S is complete. But not that. Since it is Cauchy in S, right? You are using the same distance from X. So it is also Cauchy in X. But we know that X is complete. Okay, so Sn will converge to X. Okay. Now the problem is I want this X to live in S. Is it possible or not? Why is it possible? There's some condition we haven't used, right? S is closed. Okay. So as a limit point, okay, of Sn, this limit point should stay inside S also because S is closed. Okay, and it is unique, so it must be this point. So hence, S is complete. So if you notice carefully, X, the largest space is complete. We only use in one direction. Okay, we didn't use X is complete in the forward direction here. There's nothing about X is complete here. Okay. So actually the forward direction doesn't care about whether your large space is complete or not. So meaning what? If you are complete metric space, you are always close. Okay, if you are a complete metric space, you are always close. Okay. Does that make sense? Okay. So close doesn't always imply complete. Okay. The other one. So next one. A metric space X is compact if and only if it is complete and totally bounded. Is this being done in MA or not? No one. So what's your equivalent compactness? What's the equivalent characterization for compactness? Closed and bounded, huh? Okay, closed and bounded. Let's see if we're gonna do closed and bounded. Okay, we will do closed and bounded as a corollary. Okay, so let's establish this. So compact if only if complete and totally bounded. Okay, so yesterday Joshua asked about how to think about compact. Huh? Okay, so this is one way to think about compact. Complete. Okay, you fill in all the limit point of Cauchy sequence, and then totally bounded. Totally bounded a bit like the open cover definition. Okay. Right. Okay. So yes. So there one direction is easier. Which direction is easier? Right to left. Right to left. Left to right is easier. Right, left to right is easier. Compact implies complete and totally bounded. Just now we said that totally bounded is almost like compact, finite subcover. Okay. So if we know that X is compact, what do we know? This is metric space, right? It is equivalently sequentially compact, and then what? Limit point compact. Okay. So, but we also know that sequentially compact what implies every sequentially compact metric space is actually totally bounded. Okay, remember just now we tried to do a contradiction. We pick ball from epsilon away and then we show that they have to stay inside some epsilon ball. Okay, so let's write it down for proof. Go forward. So compact implies sequentially compact implies totally bounded. Okay, so one done. Okay, next we need to show completeness. So how to show completeness? For every Cauchy sequence, okay, you must have a limit point. Okay, stay inside X. Just say limit lah, because we are in metric space, so we are fine. Okay, so suppose Xn is a Cauchy sequence. Okay. Then we have sequentially compact, right? So Sn has a convergent subsequence. Okay, converging to L. Okay, you show that a Cauchy sequence have a convergent subsequence. Does that ring a bell? Cauchy sequence have a convergent subsequence. So the Cauchy sequence must also converge. Okay, converge to where? L, the same L. Okay, so from May 1, Cauchy sequence, okay, with convergent subsequent also converges to that. Okay, so hence X is complete. Okay, how about the other direction? Wow, the other direction a bit tricky, yeah. Instead of showing the here just say compact, right? Okay, the other direction here just say compact. So what we can do is we will show sequentially compact. Okay, let's show sequentially compact here. Okay, so really if you like what we are doing here is we just show that metric space X is sequentially compact if only if it's complete and totally bounded. But in metric space these are equivalent. Okay, so let's do the other direction real quick. A bit tricky, yeah. This direction. Suppose X is complete and totally bounded. I want to show that S is sequentially compact. All right. So for sequentially compact, where do you start? start with any sequence. Okay, so just let Sn be any sequence. Okay, I want to show that there's a convergence subsequence. Okay, so how do we do here? How to cook up the convergence subsequence? What's the technique in analysis when you want to cook up convergence subsequence? Yeah, sure. Okay, need to involve sub-index. So how to pick these sub-index here? How to pick this sub-index here? So you want it to converge, right? You must pick some point that get closer and closer to each other. Anything that you can, any assumption here that you can control distance between points. What's the assumption here can control distance one? Totally bounded, right? Okay, there are finitely many balls to contain all the points. Okay, so your points are infinite, so they must squeeze somewhere. Okay. Okay. So okay, for convenience, we will rewrite Sn as Sn1. And later we're gonna build subsequence. So using totally boundedness here, we could start bound our S using ball of radius 1. Okay, by totally boundedness, we know that we just need finitely many of them. So in this case here, a very nice principle of our friend pigeonhole. What does pigeonhole tell us? You have finitely many ball, but you got infinitely many terms here. So at least one of the ball must contain exactly an infinite subsequence. Let's call it Sn2. Okay, so this is a subsequence of Sn1, and then we call it Sn2. Okay, makes sense? So we go into the ball and then pick it. What can you do next? What do you think? What's the next thing I have to do? Now ball radius 1, right? I can go ball radius half. Okay, and then go and find further subsequence here. Okay, but this half I don't simply pick. So if we so let's write down. So we'll repeat the argument. Okay, we will cover x by a finite number, of a ball of radius half. Okay, radius half. Okay, at least one of these ball must contain an infinite subsequent. Let's call it Sn3 of Sn2. Okay, I don't simply pick up. I pick from Sn2. Why? Because the number of element of Sn2 is still infinite. So this infinite thing by pigeonhole again must live in one of the ball of radius half. I don't simply pick. I don't simply go to random half ball to pick infinite term. That's useless. Okay, we need to keep continuing with this subsequence here. Sub. Okay, so what's the picture here? So if we continue in this way, what thing we have here? So if continuing in this way, what do we get? Okay, we get first, we got the original sequence S11, X21, S31. Okay, and then in the ball of radius 1, I pick S12, S22, S32. Okay, and then reading SN2, I pick S13, S23, S3, S33. Okay, so you can see that each sequence here is a subsequence of the preceding sequence. It's a sub. In particular, each ith row here live in ball of radius what? Can you find a formula? Each sequence here live in ball of radius what? 1 over I. Okay, each I. Okay, in 1 over I. Good. So what's the convergent subsequence here? What do you think? What's the convergent subsequence here? Like this, going down. Is it enough to pick this? Is it enough to pick this one? Let me think. Is it enough to pick this? Is it enough to pick this? Could you repeat if you could this term repeat or not if you pick the same position? This term could repeat it, I guess. Okay. But if you try and pick the diagonal one, you will make sure that you are increasing. If you pick the same row, I guess it could repeat, right? Maybe this one stay in every ball. This naughty guy maybe stay in every ball. But if you pick in a diagonal way, because of this subsequence property, right, you will make sure that it's increasing. Okay, it's increasing because the second one is the subsequence of the previous one. Alright, so you will make sure that you will increase. Again, not sure how it increase, but it will definitely increase. So instead, we will pick the diagonal sequence. Okay, a bit like the diagonalization argument. Before, I think that one we used to show that the limit is not in there, right? Okay, so if we pick, sorry, if we pick this yi such that yi equals to sii, okay, you need to check that actually this is another subsequence of the origin sequence. And in particular, that get as close as possible. I mean, lying in the ball. So okay, so let me write down. So for every I, okay, this yi here will live in the ball of radius ii. Okay, I don't know where is the center lah. Can I not specify the center for you? Not sure where's the center. Doesn't matter. Leave some ball. Okay, ball of some center. Is it okay? Okay, so we assume that the space is complete, right? If this is a Cauchy sequence, then we can use completeness to show it converge. Okay, then this is our convergent subsequence. Okay, is this Cauchy or not? Okay, so the claim is actually yi is Cauchy. Okay, so to show yi is Cauchy, there's really one way to show it, right? Okay, so you need to show that yi yk, okay, could live in some ball of distance that gets really small. Is it possible? Is it possible? Is it possible? Find J and K large enough, then such that their distance is less than some epsilon. I mean, every epsilon you do find such JK. For any 2 points here, where can we bound them actually? Okay, so let me write down some construction here. So for, let's say, large enough JK, how large is it? Let's say we fix 2 over n here. If you ask me why 2 happen here again, you should think about triangle inequality again. We're going to use it again. But this, if we have this J and K, if we look at these 2 guys here, Yj, Yk, then where they live, how do we pick them actually? How do we pick them? They might be living in some ball of radius less than 1 over 2n, right? Okay. I mean, the largest ball they could live inside is B of 1 over 2n here. And there's some y. Let's write down this y so that you can do triangle inequality later. Okay. This is possible, right? Because how do you know, just can you imagine how we pick just now? So we start with radius 1 ball. Okay, radius 1 ball. And then we pick the SN2 guy inside one hole, right? Pigeonhole. And then we cover this set again using a smaller ball, half ball. Okay, but obviously there might be infinite sequence living in different half ball, right? But which one are we interested? We're only interested in the half ball that contain the SN2. Okay, maybe SN3 coming from this ball. Okay, and so on. Okay, you use. So actually, you see, the thing you pick, the point you pick over is really come from the same ball. Yeah. Okay. So this is how we fix this. 1 over 2n. Okay, but then how do you compute then? So what's d of y, j, and yk now? Less than equals to d of yj to y, and then plus y to yk. Okay, but they both live in the ball of 1 over 2n from each other, which is less than 1 over 2n plus 1 over 2n less than 1 over n. Okay, so how do you pick? For every epsilon, just pick an n such that n is greater than 1 over epsilon, then you can do this and find this JK. Okay, so this is Cauchy. So since x is complete, so we go from subsequence to Cauchy sequence and then complete. It follows that this subsequence here converges. And this is the convergent subsequence that you want. Okay. A bit involved, but very standard proof in the analysis. Okay, I think I got hope. Let's go. So corollary. Okay, if you heard about corollary, that means this proof is not too long already. So this is actually a generalization of what we call the Bolzano-Weierstrass. You know what Bolzano-Weierstrass is? Huh? Anyone can recall Bolzano-Weierstrass? Complete implies closed and bounded. Is it? Hi, Larry. Yes. Every bounded sequence. Just a second.
Every bounded sequence.
Okay.
Convergence.
Every bounded sequence have a convergent subsequence. Okay, good. So this is a generalization. So a subset X of a complete metric space. Okay, because R is a complete metric space, right? Is compact if and only if it is closed and totally bounded. Okay, if and only if it is closed and totally bounded. Okay, let's quickly talk about this. So what have we established? So we say that X is compact. What have we proved just now? If and only if it is complete and totally bounded. Okay, so compact implies, so let's write down. So we have just proven that, let's do this direction. Compact implies closed and totally bounded. Hey, wait, no. Compact implies complete and totally bounded. Okay, so we got totally bounded. How to get close? Still remember how is it closed in a complete space? Because it is complete in a complete metric space, so it is close. Okay, so this complete part implies close. Okay, because it's a complete in a complete space. Okay, how about the other direction? So close and totally bounded implies compact. So previously, how do we go from close to compact? Did we go from close to compact? Not quite right. Close can imply what? Okay, close can imply complete because close in complete implies complete. We want compact, huh? How far are we from compact? Still need totally bounded. Okay, so how to get totally bounded? We have totally bounded, right? Okay, so complete, so all the way plus totally bounded. So we still have totally bounded. Totally bounded. Okay, using the previous result we have. Okay, make sense? Okay, good. Okay, next. So yeah, okay, so theorem. Okay, if K is compact subset of a metric space, then K is closed and bounded. Okay, so there's one direction only here. Okay, I write here there's the same proof with Rn. Can we just apply what we had previously? We apply this, what do you think? Can we apply this corollary? Do you think can or not? So can or not? But this theorem here require your X to be complete. Okay, but this metric space might not be complete. So that's why there's no two direction here. Okay, so you need to prove it. But the proof is the same as the Rn case. Have I proved it for you yet? Have I proved it for you? Why there's no proof here? As the metric spaces are host of. This one you should see in MA, right? Rn case. Rn case go two direction or one direction? Two direction. Again, maybe you need a metric complete now or the other direction. Okay. Let's see. Yeah. So corollary here. So this one, we say that this one I just left it first. Okay. Let's pour all the theorem out, and then we will call it a day. Then the corollary from the this theorem, we call the Heim-Borel theorem here. So if you look at the subset of Rn, so this is the familiar one you can recall, right? So S is closed and bounded, if and only if S is compact. Okay. Okay, so this is corollary because you can use the theorem and corollary we proven before. Okay. Because there's an extra condition here, because Rn is complete. Okay, it didn't specify, but to use previous result, you need to know that Rn is complete. So complete would imply closed and totally bounded. Okay, and then totally bounded implies bounded. And then on the other hand, in Rn, bounded is just totally bounded. Okay, so in a matrix, complete matrix space, closed implies complete. And then you can use whatever we built just now. And then you can go to the MA result. Okay, the usual Bolzano-Weierstrass. Okay, so this is one of the example that we do theory top down. Okay, so down to up. Okay, so this is an example of we doing theory top to bottom. Okay, we do it for complementary space and then matrix Rn, and then we specify into property on the convergence sequence. Okay, sometimes people will call these property that you had in this theorem, right? Call it the Bolzano-Weierstrass property. Okay. If you can show that every bounded sequence in your space has a convergent subsequence, we will say that that space has a Bolzano-Weierstrass property. Okay, so I make this mind map for you. Okay, someone said that I should make a mind map, right? But this mind map is written long time ago, but nonetheless made by me. Okay, so this specify what's the relation, okay, between all the words that we have discussed about. Okay, compact, limit point compact, and sequential compact, and then with closed, complete, bounded, totally bounded. And then how they are linked together with the theorem. And then in what extent they are true. Okay, I specify that I use a red arrow for metric spaces. Okay, you can, if you are red, you can use a metric space to go. And then blue one is just for topological space. Obviously, if it's work for topological space, metric space also works. So if I write metric space only because topology don't work. Okay, and then how these word related to compact. Okay, so there's 很多三角关系在这边了，大家注意一下。Okay.
Dotted line.
Dotted line. What's dotted line? Dotted line meaning you can go through from a longer pathway. I think so. Yeah. Yeah. Yeah.
Is there a LaTeX version for this?
Is there you can call Ventron kind of term.
Because I haven't seen it.
You haven't seen it.
Maybe I can help out.
Not too hard. This one use ticks is enough. Tick CD. All right. See you next week.